Hello and welcome to Mathematica Experts Live Numeric Modeling in Mathematica. Let's go ahead and introduce today's panelists. On the end here, we have Paretosh Mukasey. He is a Mathematica kernel developer with an emphasis on solving differential algebraic equations. Next to him, we have Jim Adduci, who's also a Mathematica kernel developer, who's currently focusing on numerical optimization. And lastly, to my right is Sasha Pavlik, who is also a Mathematica kernel developer working on special functions and probability in statistics. Joining us remotely, we also have Rob Knapp, the Mathematica numerical computation manager. He'll be chiming in a little bit later to help answer some of your questions. So with that, let's get started. First up, we have Sasha Pavlik, who will be talking with us today about mathematical numerics and special functions.
Thank you, Dan. Welcome, everybody. I'd like to, I'd like to say about why Mathematica is really a great tool to do numerical modeling. It provides the convenience of a task-oriented superfunctions, which pack extensive set of algorithms and provide for automatic algorithm selections for algorithm which is optimal for your problem you are asking for and is also most efficient. It also features performance by use of efficient libraries like GMP, LAPACK, MKL, etc. Also implementing the latest and greatest algorithms and providing for choice between these algorithms which is optimal for your problem. Mathematica has a reliable arithmetic because it supports an extended precision arithmetic. Whenever you are working with efficient machine precision computations, Mathematica will fall back on extended precision seamlessly when there are double precision exceptions. It also provides all the tools a numerical modeler needs in order to achieve the task he has at hand. So with that, I'll start with overviewing the representation number and speak about the arithmetic, which is basically at the core of numerical computation. So when we have a real number, it's encoded as some sequence of digits d here with some particular base, and there is an exponent which records a scale of that number. This information can be retrieved using real digits. With the double precision floating point numbers, which is typically recorded in the base 2, the number of digits is strictly 53 and the exponent is jammed to be between this number. So this means that there is a smallest positive number and the largest positive number representable in a double precision IEEE floating point numbers. And these numbers are listed here. When we go to extended precision arithmetic, there is no limitation for the number of digits. It's basically only limited by your memory, but there are limitations for the exponent. The maximal and the minimal exponent for the positive real numbers are given here, and whenever Mathematica performs arithmetic operations which cross these boundaries, an overflow will result when we cross it from above, and underflow will result when we cross it from below. When we are dealing with when we take, say, a largest machine representable number and multiply it by 2, it will no longer be possible to represent it as a machine number, and therefore Mathematica seamlessly switches to extended precision, which you can see here with that precision there, and provides for you to possibility to carry on these computations. When you input a floating point numbers, which you would need to do routinely, and enter a small number of decimal digits, Mathematica automatically interprets that as a machine precision number. When you continue and type more digits, then Mathematica understands that this is an extended precision number. If you ever need to type in a number which has a small number of significant digits but some precision, then you would need to use a double backtick to specify the precision and double backtick, so to speak, to specify the accuracy. So here's, for instance, 234 is understood as a machine number. The next number is an extended precision, and this number is specified to 20 decimal digits. This is specified to 16 decimal digits after the floating point, and that is an inexact 0. When a precision is very small and there is no significant digits to extract, Mathematica will display that number pinked and provide a message that no significant digits are available to display. So now it becomes important, we need to introduce a notion of precision and accuracy of the numbers to explain the rest. So for that, we will define two numbers. One of them would be some positive number, which will contain exactly 29 decimal digits after the dot, and some zero number. So let's introduce, and we should also think about these numbers basically as a sort of an interval, because if you think of all the real numbers which contain many more digits, we will identify all of those numbers with this number where the decimal expansion sort of is the same. So for a given number, a precision is a measure of this relative uncertainty of the value. We will say that inexact number is some exact number in the middle of that interval, and 1 multiplied into 1 plus or minus an epsilon, where epsilon is defined in terms of precision of a number like that. The accuracy is a measure of an absolute uncertainty, and therefore no multiplier is needed here. And it is defined, as they are defined in such a way that their difference always measures a scale of the value. So real exponent, so let's actually evaluate the precision. Let's see, the precision of a number x is a little higher than 29, which is a number of digits here. Precision of a number y is exactly 0 because a relative uncertainty is not defined. The number here is 0, and you multiply 0 into whatever you get 0. The accuracy of x and y here are defined, and they are both exactly the same because there are 29 digits after this. And the real exponent for 0, of course, is not defined. The real exponent of x, which is the difference of those two numbers, will give you the same thing as a base 10 logarithm of a number. So with that, I need to go on and bring up a notion of two special precisions in Mathematica. Dollar machine precision is an extended precision such that there are exactly 53 binary digits in it. So it's basically an extended precision equivalent of a double precision IEEE number. And a simple machine precision refers to that double precision number. So say if we set exact 1 into machine precision, we get a double precision number. If we set it into a dollar machine precision, we get extended precision number with the same number of binary digits. It is also important to realize, for the reasons which will become clear later, that the machine precisions are treated as the lowest precision available. So if you're asking for a precision of this list, which contains precisions of two different things, Mathematica will pick the minimal precision, and in this case, the minimal is machine precision. Although machine precision sort of is, when you replace it with an extended precision, you will get 5 as being the lower precision. So this is important to keep in mind. Now, when Mathematica performs an arithmetic operations, we can encounter a loss of significant figures. For instance, imagine that you are adding two numbers which are close but opposite in a sign. In that case, most of these digits will cancel, and actually the reasonable expectation is to expect any software to return the small number of significant digits. And Mathematica, in fact, does. It tells you that the number of significant digits in this number is only 2.8. Now, this is achieved through a precision tracking. Mathematica automatically keeps track of precision and sort of reduces the precision when it detects these cancellations. It is, it is a common practice to do a fixed precision computation likewise, and in the cases when such things happen, then the remaining digits are somewhat ambiguously filled with 0, but this is a convention. So in the fixed precision computation, you get that. Now, a significance arithmetic refers to how Mathematica keeps track of this precision, and it does this by using linearization of the error. So when you multiply two numbers, the exact error would be given by this polynomial, where when we linearize it, we discard this term, which is much smaller typically. Well, addition is done exactly, but the power is also doing this linearization. So in order to appreciate the usefulness of significance arithmetic, we will consider a tent map, which maps a unit interval into a unit interval. When we perform this using an exact arithmetic, you will see that these numbers sort of become a subtraction of a subtraction of two numbers, and these numbers will increase in scale as we progress in the sequence. And therefore, we will encounter this same cancellation phenomenon, which we will see in, just now. So imagine that you would start here with in machine precision starting value, and we'll continue to iterate. And we will plot here a log scale sort of difference between numbers obtained here using machine precision and the exact numbers evaluated to precision 50. And you see that the sequence will deteriorate precision as we go on, which means that after 50 iterations, basically no correct digits are left in the answer. When we will repeat the same computation with dollar machine precision, which by doing so we enable precision tracking, we will see that the precisions of the numbers become smaller and smaller, and ultimately in the end we only get one correct decimal digit. We can use a dollar mean precision in order to turn off a precision tracking below a certain value, and that's exactly what's happening. And although these digits sort of are not correct, maybe not correct, we ask Mathematica to keep them. Now, the nature of error estimate in significance arithmetic is pessimistic. So you can actually get you can notice that you get a lot more correct digits than the Mathematica tells you, and it is important to realize when that happens. So an example would be any stable procedure, numerically stable procedure. So let's consider the largest eigenvalue computation by essentially iterating the matrix and renormalizing the result. So here we have a code which performs just that. We do a fixed point multiplication of a matrix into a number divided, into a vector divided by its norm, and we start with a random number. So we will consider a 4x4 Hilbert matrix and try to evaluate its eigenvalue. Excuse me, I have to define that. Its eigenvalue to 47 digits, we get exactly that. Now, if we do the same computation without fixed precision, just using our variable precision computation, we will see that the number of correct digits reported is less, although we will see that these numbers are correct. And we can ascertain that by solving the problem using exact algebra in Mathematica and numerically evaluating the result, and we see that all of the precisions are correct. So sometimes it is beneficial for the efficiency's sake to use fixed precision computation, but that is only safe to do when you know the problem is stable. Now, in order to proceed on, I need to say that in addition to numbers, Mathematica has so-called mathematical constants like a pi and e, and those are, you can think of them as symbols which act like number, which means that you can take any of those numbers and set them to any requested precision, or say to 150, and Mathematica will compute the value of that constant and return it as an approximation. Now, using these mathematical constants, you can build more complicated expressions which are needed for your modeling. A numeric function would be a function in Mathematica which evaluates on the inexact input. So when you feed an inexact input into a sign, it will get you an inexact output. Likewise, do special functions or other functions. You get inexact complex number and get their absolute value out. Now, another feature of numerical functions is that their output tracks the precision of the input. Consider an arctangent, and we will evaluate it with a machine precision. We get a machine precision out. Now, we will set that to precision 16, and we will get a precision 16 out. And now, as we increase the precision of the input, the precision of the output tracks it and gets back the result. So here is a little manipulate, which will take different functions and different argument to it, and will show you how the precision of the output changes with the precision of the input. And you see that they are all linear, right, with the different slopes. So that allows us, for instance, to do things like try to evaluate an explicit exact number to a requested number of digits by essentially feeding it arguments which are more and more precise. Now, the total number of numeric functions in Mathematica is well over 200. So we can get that, extract them in the system context, all of those numbers which have attribute a numeric function a constant. And for your later perusal, this is the entire list, which is clickable into documentation, so you can look at what it does. Now, precision of the output in a numeric function may be smaller than the precision of the input. And to consider such an example, we will look at a finite difference approximation for a derivative. So this particular code constructs an approximation using forward difference with step h, and will construct an approximation of the derivative of order p of a function f of x, univariate function. So let's evaluate that function and consider an example. We will take a black box function f of x and construct an approximation of an order 2. When we use a symbolic nature of Mathematica to verify that, you see that indeed expansion gives you a second order derivative, and the error term here is h to the 3. So that's accurate, up to h to the h squared. This is an accurate representation. So now let's try to use this in order to do a numerical computation of a derivative. So let's take a special function Fresnel and try to evaluate its second derivative using the step of 10 to the minus 6 at some point, which is, the precision 30. We get that the precision of a result is actually 16, so we've lost 15 significant digits in doing so, and using the direct function of derivative will get us a lot more digits. Now, approximating higher order derivatives will give you bigger precision loss. So say order 4 here, you lose 16 digits, so you only get 5 digits correctly. So now suppose you would really want to compute the fourth order derivative using this finite difference method, but you would want 30 digits out. In order to get that, we have a wonderful function called n, which finds the numerical value of the expression. So let's evaluate a symbolic expression for that fourth order derivative and produce a black box function which takes in a real, prints the precision of the input, and computes that approximation. So now when we evaluate something to a precision 30, we'll get back what we had. Now, if we ask n to do stuff, then we will actually see that the Mathematica automatically raised precision in order to get us the necessary precision, requested precision of the output. We can limit how much of a precision n will raise by using the $max extra precision, and that's seen here. If we are asking for a precision 10, evaluating with a precision 30 will produce a message that that's impossible. So setting locally max extra precision will let you do the job. I would like to wrap up now and sort of consider a nice example of trying to build up a function which is based on our super solvers. So many of our this numerical solvers like nintegrate, ndsolve, and minimization, find root, and all of the others take a working precision. And the working precision option essentially lets you specify the precision of the intermediate computations. But it doesn't really mean that the answer will be given to that precision. The actual precision, precision of the output is controlled by two options, precision goal and accuracy goal, and with them specified, Mathematica attempts to get a numerical error of the result to be less than that. So consider here a functional of functions of real arguments which computes a norm of LQ norm of real functions, and some features of this is we take that q, which is supposed to be a real number, and we take a function and a symbol x. We compute an input to an integral. Now, in doing this computation, Mathematica can actually lower the precision of the expression. So in order for nintegrate not to complain, we have to specify the working precision, which is a working precision of this input. Now, we raise a max recursion to get some number back, and once we obtain the result, we want to lower the precision of the result in order to ascertain that the number of digits actually are accurate. And this is a safeguard in case when nintegrate will return and evaluate it. So we've evaluated this, and let's try to see what it does. We will compute a 4 norm of such a function with a machine precision number, with an extended precision number, and we see that it does exactly track the precisions. So we can actually plug it into an N framework and obtain the values of the pi norm of PDF of gamma distribution and get some value out of it. Now, I wanted to sort of wrap up with trying to sort of do an LP norm of another PDF of a Laplace distribution, and you'd see that a curious feature of it is that it attains a minimum here, and we want to know where that minimum is. So we will be able to plug in this numerical function we've constructed into a find minimum, say that the minimum is somewhere between those 2 points, specifies a working precision, and the Mathematica will obtain as a value of the minimum as well as a position of the minimum with a requested precision. So with this, I'd like to thank you so much for attention, and back to Dan.
Well, thank you very much, Sasha. Someone submitted a question. What does fractional precision mean?
Well, a fractional precision, so as we would look back at the precision is actually something which is relative to the value of the number, as we will see here. So that means that if your number here is not an exact power of 10, for instance, then the scale of that number is fractional, so precision can really be fractional. But in addition, it is worth reminding that the representation of real numbers in Mathematica is binary, and the precision you are asking for typically is decimal. So the conversion between these two involves multiplying into a logarithm of 10 base 2, which is itself inexact. So it's natural to get inexact precision out. Thank you, Dan.
Excellent. Thank you very much. And for more information about all of the things that Sasha just talked about, feel free to log on to reference.wolfram.com, and you can get a lot of great examples and information. Up next, we have Paretosh Mukherjee, who will be talking with us about solving differential equations in Mathematica.
Thank you, Dan. Okay, so today I want to talk about how we use a framework in order to solve different kind of differential equations in Mathematica. So the topics I want to focus on today is basically give you an overview of the framework that Mathematica internally uses, and provide you a number of examples for the various kind of problems that can be solved within this framework, and finally give you a list of resources where you can go and get a lot more information, because I might not be able to cover everything. The framework which Mathematica uses internally to solve differential equations is called the ND-solve framework. ND-solve in itself means it's a numerical differential equation solver, and within the single framework you can solve a vast number of problems. So you can solve ordinary differential equations, partial differential equations, boundary value problem, delay differential equations, hybrid systems, differential algebraic equations, and parametric differential equations, and various combinations of such. And I'll show you examples. I'll try to touch on several of these different types of problems. One of the things that is remarkable is that ND-solve's output after it solves a differential equation is not just a number of points that you get, but rather the output comes in the form of an interpolating function. So you can take that information and then perform more calculus and more analysis from it. So it's a very useful thing to have, and it works seamlessly across different Mathematica functions. So with that, let's look at the ND-solve framework itself. The framework consists of several functions, the most common and the most used being ND-solve, and then it has several cousins. You have ND-solve value, parametric ND-solve, parametric ND-solve value. You have certain functions that can be used with ND-solve, and these main functions called when events, discrete variables. And you also have a few utility functions that allow you to control the internal data structure that ND-solve uses to solve the problem. I'll try to go through these functions by using a few examples. So the first example that I want to cover is, well, the most common one, which is how do you solve ordinary differential equations in Mathematica. And you'll see that the general syntax in order to solve this, these ODEs is as follows. You have ND-solve or ND-solve value. You give with equations. Now the equations themselves will consist of the actual differential equation and a set of initial conditions to specify the state of the system. You give the number of dependent variables and the independent variable. For ODEs, it turns out just one independent variable. Okay, so here's a very simple example. You have ND-solve. The first one is your differential equation. You give it a set of initial conditions, which is for x and x prime, and you give it the dependent variable and the limits of integration. So it's from 0 to 50. So when I solve this, I get the result back, as you can see, in the form of an interpolating function. And this allows, so I can take a derivative of this interpolating function. I can plug this into another function and just use it as just another function and can perform lots of analysis on this. So the most common one that you would want to do is basically just plot it. So here's an example based on solving the Lorentz equations, which is a typical chaotic dynamical system, wherein we have three differential equations, and we want to solve it for a specific set of initial conditions. Max steps goes to infinity is an option that we provide that tells ND-solve internally to use as many substeps as it needs so that it reaches that specific working precision and the accuracy and precision goal. You can plot this because this is you can plot what is called as the phase space, and you can see you get this beautiful butterfly pattern which is reminiscent of the Lorentz equations. You can, because of the simplicity with which ND-solve works as a superfunction, you can basically take this and do some analysis. And here's a visual analysis which basically looks at the sensitive dependence to initial conditions. So I'm going to solve the same problem, but now I'm going to change the initial condition for y from such that you get three solutions, one with 1.9 and 1.1. So I'm keeping x and z the same, but the y initial condition changes. So with that, I'm going to get three sets of solutions. So you can see this is the first one, second one, third one. And now what I'm going to do is I'm going to plot all of this together and see how the solution evolves. And you can see that you have three balls, each representing an initial condition. And once it starts moving, eventually it starts off very close to each other, but as time progresses, the balls go their own separate ways, which is an indication of sensitive dependence to initial conditions. So as you can clearly see, because of the automatic selection method, with just a couple of lines of code, you can basically do a lot more analysis. Okay, so next we'll talk about partial differential equations. With partial differential equations, again, the syntax is relatively the same. You have ND-solve, you have equations, you have initial conditions, and boundary conditions now, which become part of the system. Variables, you give it the dependent and the independent variable along with the limits of integration in each one of those directions. Partial differential equation, obviously, then you need to give it more information. Here's a simple example. This is just a simple transient diffusion equation. So you're giving ND-solve. Now the dependent variable u, which is what we want to find the solution from, consists of two independent variables, t and x. And so this is, d is basically takes the derivative of whatever function you have with respect to time, which is equal to the second derivative in space. And because you have second derivative in space, you need to give two boundary conditions and one initial condition. So the initial condition is specified by setting t equal to 0 over here. And so that's set equal to 0. And you have two boundary conditions, which basically say that the left boundary is going to have a value of sine of t, the right boundary is a value of 0. And you give dependent variable, and you give your limits of integration for both t and x. Okay, so you go ahead and solve that, and it works exactly as it works with partial differential equation, and which is why I keep emphasizing that this is ND-solve is basically a super function, and a lot of automation goes inside ND-solve in order to pick the appropriate algorithm in order to solve the system. And of course, you can now plot this, and you can see how the system works. Okay, so this is partial differential equation. I'll move on with some more examples. There are many more interesting examples, so I may have to skip a few. So let's go now to hybrid systems. With hybrid systems, we now introduce one more function called when event, which I sort of introduced in the second slide when I was talking about the different functions that ND-solve framework contains. So in this case, when event literally allows you to change the direction of the solution based on a certain predicate and a certain action. Okay, everything else remains the same in terms of the syntax. You have ND-solve, you give it the equations, the initial conditions, but the only thing you now add is what is called as a when event. And it's pretty intuitive in terms of when something happens, perform a certain action. So the standard example we like to use is the so-called bouncing ball example, wherein you drop a ball from a certain height and you watch it bounce as it goes over a flat plane. The way you control the bounce back as it hits the plane is you basically say that whenever the ball hits the ground, which is a y of t equal to 0, by the way, y indicates the trajectory of the ball. So whenever the ball hits the ground, which is y of t equal to 0, reverse the direction of the velocity and decrease the velocity value by a certain amount, so that you also have this realistic damping effect. So now I'm going to go ahead and solve this, okay? And you look at the plot, and there you have it. Now, of course, you can make this arbitrarily complex by setting in all sorts of bells and whistles in order to, overcome the so-called Zeno effect, so that the ball doesn't go bouncing infinite number of times, and so on and so forth. So here's an example again from the field of dynamical systems, where you might be interested in looking at what is called as the Poincare section of a certain differential equation. And in this case, the event that we put it together is whenever the time crosses some multiple of 2 pi, we want to extract the x and the x prime solution at those instances. And we're going to let it run for a really, really long time. As you can see, we're letting it go from 0 to 100,000. And after the solution is done, you can see that you get this beautiful Poincare section coming out from it. All right. So now we will move to parametric differential equations, which is another way of addressing a broader class of problems, which is how do you deal with differential equations wherein you have a parameter embedded inside the differential equation and you are interested in modifying this parameter and looking at how the solution behaves. The most common example or the place where parametric differential equations are used would be you have a bunch of data which you might have acquired from an experiment, and you want to fit perhaps a differential equation through it. How do you do that? Well, with parametric ND-solve, it becomes very, very easy to do it. So the syntax essentially remains identical to, or rather same to the original NDSolve syntax, but with just one addition. So you have parametric NDSolve as the function name. You give it all the equations. You give it the dependent variables. You give it the independent variables, and finally you give it an additional set of parameters. These are the free parameters that will take certain numerical values and then from there extract the actual solution. So here's a simple example. You use parametric NDSolve. You have a second order differential equation wherein you give initial condition for x, which is set equal to 1, but x prime is taken to be this free parameter. So then you give it the dependent, independent variables, and now you say that parametric NDSolve, please take this variable s as an open parameter. When you go ahead and solve this, the result is not the form of an interpolating function, but rather a parametric function. And this parametric function takes whatever arguments were specified in PARS. Okay, so in this case, since it's supposed to take only one parameter, when I say x, give me the numerical solution of this differential equation when s takes on a value of 1.5, you see that for that specific s value, you get an interpolating function back. Okay, and so of course you can take that and you can go ahead and plot it. Now the advantage over here is there's a lot of caching going on behind the scenes, so that you can modify the parameters and it'll very efficiently calculate the solution for different parameters. So for example, I can change this from 1.5 to 5, and there you go. It happens very, very fast. Okay, because this again has the same concept of just treat it as a black box function, you can take this parametric function and ask the question, well, what kind of a solution can I expect when I specify that the solution I want at the end of the integration, x equal to 10, I want it to be 0. So give me the parameter that will give me this condition. And you can set this up inside a find root, which is one of the optimization functions, and it tells you that for a value of 1.40296, so let's put that back in here, 1.40296. Of course, there are more digits here, but for now we'll just take that. You can see at x equal to 10, it goes very close to 0. So here is one example that we have where we are going to fit parameter to data. Okay, so here is synthetic data that I made up. Okay, and I'm going to plot this, and hopefully you can see that it's got a bunch of dots, but there's a definite trend and a structure to it. Now the objective for me is to fit a differential equation that passes through this, or rather is representative of the experimental data points that I have. So I'm going to choose a differential equation of this form. So I have y double prime equal to negative y times this w, and of course I don't know what the initial conditions have to be, so I'll keep those also as my parameters. So what we're going to now use parametric NDSolve is to find the value of w, a, and b. So the first thing we do is we set up the problem. We use parametric NDSolve, y double prime equal to negative w times y of t. Give it the initial conditions, dependent variables, independent variables, and we now have three parameters, w, a, and b. When we get the result, I'll remove the semicolon so you can see the result. You get a parametric function similar to what we had before. Now what we will do is we'll take this function, put this inside a find fit, and see what solution we can get that will minimize the data. I have already pre-computed it, but it takes just less than a second to compute it already. And you can see for these values, it seems to be a good fit for the experimental data points. And you can plug these values back in, and you can see when you plot them along with the data, you can see that it's a pretty decent thing to do. I would like to emphasize, and this is quite important, that these kind of problems are typically non-trivial, but with this entire encapsulation inside of NDSolve framework, we are able to perform these kind of analysis in just 2 or 3 lines of NDSolve code, which is very, very critical, and you can expand on the system to make your system as complicated as you want or as simple as you want. Okay, with that, I want to now quickly talk about resources. Now, obviously, I haven't really covered. I've just scratched the surface of the NDSolve framework, There is so much that can be done, but because of the time constraint, I'm going to have to move on. So differential algebraic equations was one area. I'll quickly go over it. It works exactly like ND-solve, but differential algebraic equations are a special breed in itself in that they require a lot more analysis. So the two options that you'll get is that you can solve DAEs, or you just give it as a regular ND-solve, or you give it ND-solve and you have to add this special method which says index reduction goes to automatic. I won't be able to go through the example, but I will tell you where to look for a lot more information. There are three references which I would like to point you to. Go to the ND-solve reference page. There are a number of tutorials associated with ND-solve that details just about every single thing, including some of the internal algorithms that we use to solve various kinds of problems. Okay, with this, I'd like to conclude my talk. Thank you, Dan, and back to you.
Excellent. Thank you, Paritosh. And just one quick question that we've gotten from a few people already is how do you tell ND-solve to use a specific integration method?
Right. So that's a very good question. Okay, so what I'll do is I'll just take, I hope everybody can see this. I'll take something rather trivial. I'll say x of 0 equal to 1, x being my dependent, from t being my independent. And now I want to solve it using an explicit Runge-Kutta method. So I'll say time integration goes to explicit Runge-Kutta. And that's pretty much it. Go ahead, it solves it. So using this option, and of course you can change this, we have various canned routines, and if you're a little bit more hands-on, you can develop your own integration method and plug that inside ND-solve. We offer great amount of flexibility for user to put their own integration solver if they want to.
Excellent.
Yeah.
Well, thank you, Paritosh.
Sure, my pleasure.
And for more information about everything that Paritosh just talked about, including those reference links that he just gave, you can visit reference.wolfram.com, and there's a lot of great material there. Up next, and up last, from our panelists today, we have Jim Adduci, who's going to be talking with us about numerical optimization in Mathematica.
Okay, thanks, Dan. As Dan said, I'll be speaking about optimization in Mathematica, specifically numerical optimization. So I don't know if we'll have time for too many applications, but you've already seen some. Sasha, I think, used find minimum during his talk, and I think Paritosh used find root, which, although it's not exactly an optimization function, uses a lot of the same techniques. So I've compiled here a list of some of our main optimization superfunctions, 5 of them, and we'll go over and talk about how to use some of these. There's a lot of overlap between these functions, so find minimum and nminimize can both solve constrained optimization problems. So it's important to pick the proper tool for your optimization problem. I don't know if I'll go through this whole decision chart, but this is in the documentation. It's good to sort of think about your problem before you pick the tool in Mathematica. If your problem's linear, you want to use linear programming. If you need a global optimum, you should use nminimize or possibly minimize. And if you just want speed and local optima is okay for you, find minimum is probably the proper tool. And also I should mention that each of these optimization tools, find minimum has a twin function, find maximum, or nminimize has a twin function, and minimize has nmaximize. So they basically do the same thing. All right, so let's just dive right in to, here's minimize. So minimize, if you give it exact values, will give you the exact global optima. So let's just run so this one gives us a daunting looking expression for the solution in terms of some roots. But if we plot it, we see that actually, it did find the maximum. So I won't spend too much time on maximize. Actually, what happens if you use maximize and you don't give exact values, if you give numerical values, it will just go ahead and call nminimize, which we'll talk about a bit later. So for linear programming in Mathematica, we have the function linear programming, aptly named. So what linear programming does is it minimizes, a linear objective function, c dot x here, subject to a linear constraint. And this is an inequality constraint here by default. And also there's a default that the variables should all be positive. So let's jump to a basic example here. So C is my objective function, M is my matrix of constraints, and B are the right-hand sides of my constraints. And so I just push them in one at a time into linear programming, and it gives me the solution. And I've hidden the Mathematica code that generated this picture. It wasn't terribly long. And you see that the optima, here's the polytope, and the optima is actually on that corner of the polytope, which you would expect. Now, there's a lot of different types of special types of problems in linear programming that Mathematica can handle. For example, if you give exact values, again, linear programming will give you the exact solution. So you see we got the exact solution there. If I had just put a decimal in here, I would have gotten the numerical approximation. We can handle large-scale problems. Now, these should be entered using sparse arrays, sparse problems. Linear programming has interior point methods which can take advantage of the sparse nature of the problem. I won't run this, but you can see that this is a very large problem. Looks like 10 to the fifth variables and 10 to the fourth equations, and it handles it in about 5 seconds. Now, also, we can handle integer constraints. So if you want a particular variable to be constrained to be an integer, you just have an extra argument over here, and you say the first variable should be an integer, and it will do the integer linear program for you. Okay, so let's move on. Now, if you're happy with local optimization, if you don't need the global solution, you just want a local solution, find minimum is probably the best bet here. So let me just give you a simple example. So here's a function that has one global minimum right here and several local minima. And if I put that function into find minimum and I give it an initial guess here of 5, as I described, it'll give you a local optima. It's giving me the value near 6 here. As a good example problem, we have the Rosenbach problem, which is a good problem for optimization because it has a long, thin valley, and it's easy for optimization algorithms to get lost in there. So it's a good test algorithm. So let's run find minimum on that, and it gives us the solution at 1, 1, which is correct. Now, there's several ways to sort of peek inside and see what steps find minimum has taken. First of all, you can add a step monitor in there. Now, a step monitor, you just put it at the end, and you use rule delayed, and you tell it what to do, and it will do this at every step. In this case, I'm telling it to print the values of the variables at each step. So I do this here with the Rosenbach example, and I get printouts of all the steps. Now, a lot of this actually can be automatically done with the package unconstrained problems here. And if I run the same one, it gives me a lot of data about how the problem was solved. There's 15 steps, 21 function evaluations, and you can also get gradient evaluations. And the different colors here tell you what type of evaluation happened. So let's move on to global optimization. So a good function to use for global optimization here is nminimize. Although I should mention another good strategy if you know a lot about your problem is to just use find minimum at a random assortment of points. And nminimize does something like that internally. So let's just do the same simple example we had before, where before find minimum caught a local minimum, nminimize quickly picks up the actual global minimum. And there's also a method option here. So if I say method goes to, let's say random search is one of our algorithms, I get the same. So there's a method option. There's several methods. There's a simulated annealing method. There's differential evolution. There's random search. And there is Nelder-Mead. I think Nelder-Mead was the default on this problem. So moving on to constrained optimization. Now, both find minimum and nminimize can handle constraints. Find minimum uses interior point methods when there's constraints present. So it automatically switches to using an interior point method. And nminimize uses basically penalty methods to handle the constraints. So here's a problem where I've got my objective function here, and my constraint is that the L1 norm of the variables should be greater than 1, so it should be outside of a diamond-shaped region. So solving this problem with find minimum, you can see that we start here, and we jump to a local minima almost immediately. Now the same problem, and by the way, I just used a contour plot here and overlaid the steps which I showed using a step monitor to get this visualization. Now the same problem with nminimize, we would hope would go to the global minimizer, which is down here. And in fact, it does. It jumps right over the constraint and lands in the global minimum. And similarly, we could have added all the other methods that I looked at did the same thing for this problem. So it's rather robust. So here's just a quick example of how you can take other functions in Mathematica and easily integrate optimization into them. So here's parametric NDSolve, which we just saw Paritosh describe in his presentation. So I've given a parametric differential equation here with a parameter a in the equation. So there's going to be lots of solutions corresponding to different values of a. So let's plot those solutions for different values of a. So here they are. And the question here is, which of these solutions has the minimal arc length? So if you look carefully, I actually also solve for the arc length in my parametric solution. So I've got this value alpha that gives me the arc length. So let's plot those arc lengths versus the value of a. And we get this interesting shape. It looks like the minimum is near 0, but there's this other local minimum down here. So let's find that global minimum first. Actually, it wasn't at 0, if I recall correctly. It looks like it's just to the right of 0 when I zoom in here. So let's find that minimum, and it turns out, yeah, it's at about 1/1000th. It's at 0.00189. And let's evaluate the functions around there and see what they look like. So you can see, as I perturb a little bit, I get these solutions that have bigger arc length, and I've sort of lightened them in the plot. So let's go back here and let's look at what this local minima down here looks like when I plot the solutions. First, let's find it. Let me open this up. Okay, it's at about 0.725, which is what we would expect from this plot. I'm using find minimum here. And now if I plot the nearby solutions, I get this interesting behavior where if I perturb it, I get a lot of deviance towards the end, even though all the solutions for nearby A are very close together at the beginning of for small t. So that's about all I had. We're running low on time, I suppose.
Excellent. Well, yeah, we want to make sure to leave plenty of time for Q&A, but actually I had one question that already came in for you, which is for large nonlinear optimization problems, is it better to use nminimize or find maximum?
Okay, so that's a good question. If it depends on a lot of things. If your problem is constrained, you could probably experiment with either, and you could either you still want to go with find minimum. It handles large problems a little bit more quickly. Or if you need a global optimizer, what you can do is find minimum at a lot of random points. Nminimize might be a little bit slower for large problems. Now, if you have an unconstrained problem, find minimum will definitely be faster. And especially for large problems, we'd recommend using find minimum for unconstrained problems.
Excellent. Well, thank you, Jim. And for more information about everything that Jim was talking about, you've probably heard it by now, you can visit reference.wolfram.com, and we have all the information there, all the great examples. And I want to make sure to leave plenty of time here for Q&A. So next up, we're going to bring on Rob, who is our manager, who has been joining us remotely, and he's been keeping an eye on all the questions you've been asking. So Nicholas has asked, can you tell us a few examples of numerical algorithms that are used in Mathematica that were developed according to or use Wolfram's search of the computational universe?
Okay, so Stephen Wolfram wrote his new kind of science book, and a part of that, and part of the research for that was sort of trying to search the computational universe for various algorithms. And I think that's affected Mathematica in two ways. One is just doing that search and being able to work that search in Mathematica gave us a lot of experience with working with different kinds of algorithms. And so as a result, we've become very good at setting up things to select between different kinds of algorithms. Another type of thing are some algorithms that are actually directly used in Mathematica. And I think the best and probably the strongest example of that is a random number generator. So if I do seed random of, say, some number, and I can't remember what the methods are, so I put in method as question. This is not, That's okay. That's a bad syntax. It should give me a list of which. Okay, so no, I have to give a specific method. Method goes to CA. Okay, here we go. So now this is the one I had to put in a string. But this tells me what generators we actually have available. And you'll notice there are 3 that use particular cellular automata algorithms. Those are result of Stevens. And actually our default random number generator is what we call the extended CA generator. So if you use just the random number generator, say like random integer of 1, 10 to 7, comma. Say something like that. That'll generate, random integer of size 10 to the 7th. And the bits for that go into that random integer come from the cellular automata generator. And now you can change methods, same or send twister, but the cellular automata generator has passed all the sort of diehard tests, and as far as we know, it's a very good generator. So that's an example of that. So that's all I have to say about that for now.
All right, great. Well, thank you, Rob. We've got a couple other questions coming in for you. Another one is, what methods are used by interpolating function?
Okay, so there are a few questions I saw that came in on this. So we'll call it iPhone, say equals X. We'll just use my favorite. Okay, so we'll set up and I got something. Oh, I got an extra equal. Sorry, my typing is not great here. So this is an interpolating function, and actually we want the first part of that. So if you look at the input form of this, okay, it's just some, confusing gobbledygook of lots of numbers. But basically what we do by default for this is the interpolating function is based on typically polynomial interpolation, though not necessarily exclusively so. It's extensible that as we add new methods, we can add different methods of interpolating. But the default, for example, in this example, what it uses cubic Hermite interpolation. So what it does is at each step AnySolve takes, it saves the value of the function and the value of its derivative, the endpoints of the step, and it just uses cubic Hermite interpolation in between. Now you can add an option, okay, to this. If you add the interpolation order goes to all, then the interpolation becomes method dependent. And what interpolation order all means is you're actually using what's called a dense or continuous output from the method. So for the default method, this actually is it uses the Nyquist history array, because the default method for simple ODs like this is a multi-step method. So it uses the Nyquist history array to sort of generate a Taylor series from the point. Now, if you use some other more complicated methods, we have sort of a general way of generating dense output that ends up using Chebyshev interpolation, so it's quite stable. So there's a whole bunch of different algorithms, and say when you're doing a PDE, what it does is it does multivariate interpolation. So it first interpolates in one direction and interpolates in another direction. And there's also a possibility of using an interpolating function on unstructured grids, in which case it uses a linear interpolation on a triangulation. So interpolating function is sort of a great innovation for AnySolve because it incorporates a whole lot of algorithms, but basically you can just use it as a function and not have to worry about how it's interpolating. The only thing you need to ask yourself is how accurate do you need the interpolation, and if you need it to be as accurate as the method, just use that interpolation order all, and the interpolation is just as accurate as the method, both at the endpoints and in between steps. But it's a little more expensive to do that, so that's why it's not the default. Okay, that's all for that answer. Another question?
Just one more for you, Rob. We were being asked, to what extent do these algorithms make use of multi-core hardware resources when they're available on the hardware, like CPU and GPU?
Right. Okay. So that's a good question, and the answer is to some extent. So, for example, if you do a PDE problem like the one Paritosh showed, or you do a bigger one, there's going to be a lot of in linear algebra. And the same is true for, say, find minimum, find root, and minimize. There's going to be a lot of linear algebra. Now, the linear algebra is all set up through a linear algebra library, which is the Intel Math Kernel library, is what we use right now. And that automatically multi-threads linear algebra across multiple cores. Now, we also say if you So that's what's definitely done automatically. We also have a parallel toolkit that would allow you to, say, solve problems on different Mathematicas. Now, because the availability is not certain now, we don't do much more than that automatically. However, coming online in the future are going to be lots more ways to use GPUs or access GPUs when they're available, and so we're looking forward to being able to use some of those in a more automatic way. But in the meantime, we have a bunch of ways to use multi-threading in various ways. One, we have an OpenCL and a CUDA-Link packages that come with Mathematica. They're add-ons. So you can use those to actually use, to specify, so you have to do it yourself, but you could say I want to do this part of the problem, with CUDA, and there's lots of functions you can just access directly from the link. One of the issues with GPU computing, which is why we don't do it automatically now, is there's often a big transport cost between the GPU and the main memory. And when you know that transport cost is not going to be too excessive compared to the computation, that's the time you want to use it. But it's often very hard to judge that automatically. And I think tools for doing that and figuring that out are coming online. There's also, within our Mathematica compiler, you can compile functions to be automatically multi-threaded. And if you use those compiled functions, then in some of these super functions, you'll sort of get the advantage of some of the multi-threading automatically there. So that's another way you can use multi-threading, but it's not done automatically. So I think that's about all I can meaningfully say about that for right now. Thank you.
All right. Well, thank you for joining us, Rob. And we're going to actually go back to our panel here, and we're going to have a few more questions. We're going to run a few minutes over, but I want to make sure we get to some of your great questions here. So first up, I got a question for Sasha here. How do you do stochastic approximation in Mathematica?
Well, thank you. That's a good question, although it's a little vague. So stochastic approximation can be applied to a variety of problems, including optimization and numerical integration, all of that other stuff. So really, we don't have stochastic methods for optimization, although Jim would probably be better fit to say. But so I'll focus a little about stochastic approximation to n-integrate. So n-integrate does provide out of the box a Monte Carlo ways to approximate n-integrate, and the reference page does mention here several options for n-integrate. So we support a Monte Carlo, adaptive Monte Carlo, quasi-Monte Carlo, and so on. So these are available to perform a multivariate integration over large dimensions. So specifically, you could see that that's, on this toy example, it's rather fast. One thing to know about it is that as soon as, when you do a Monte Carlo, each time you hit it, you get a different answer, right? So this is not something that must alarm you. Now, if we will use a symbolic nature of Mathematica and wait for a second to get that integrate computed explicitly, we'll get this expression in radical, and we'll get 3 decimal digits. You see that exact value, so we sort of got the correct ballpark, but not the right value. And we can actually ask n-integrate to do these computations repeatedly and use histogram to plot a distribution of the values it obtains. And you see that they cluster around some mean, which is close to the true value, but they actually are stochastic and sort of resemble a normal distribution. Now, if we want to change all of the Monte Carlo methods here are actually performed using each of these variables being uniform. And if we want to change that and change a different distribution for random numbers, we have an n-expectation which supports a Monte Carlo method, and you can specify distributions of each particular variable. So here, for instance, we are computing the expected value of a special function over parameter u being uniformly distributed from 0 to pi, and the modulus parameter varying according to beta distribution. So that's, I guess, as best I can answer the question. Thank you, Dan.
Excellent. Thank you, Sasha. Another question that's come in is for Paritosh. For larger systems of ODE, can matrices or vectors be used next to indexed functions in NDSolve?
Right, and the answer to that is yes, you can. So let me show you a small example that'll demonstrate this. So what I'll do is I'll generate a matrix, call it mat. I'll just take a 2x2 system here, but of course this can be extended to a very large system. So I've defined a matrix, and what I'll do now is I'll use NDSolve x prime of t equal to mat, and now I'll use the dot product, and I'll say mat dot x of t. So this is a linear system, but of course you'll get the idea. And then I can specify an initial condition, which will now, instead of a scalar value, it will take on a vector. So in this case, I'll say 1, 2. And of course, I'll need my braces for correct syntax. So that's my differential equation with the initial conditions. I give my dependent variable, t goes from 0 to 1, and we'll just say solution, okay? So there's my interpolating function, and if I do x at 0.5, for example, you'll see that instead of one value, it returns a vector. So all this is neatly packaged inside of NDSolve for you to make use of matrix vector type of ODEs.
Excellent. Thank you, Paritosh.
Sure.
Next question we have is for Jim. Jim, how can we set a constraint for the dependent variable which NDSolve is solving for?
Yeah, okay. So this is possible. When I saw it come up on the screen, I pulled an example right out of the documentation, in fact. So what you do is you want to give a dependent variable specification. So I took the questioner's example of a variable which we know is between 0 and 1. You say dependent variables to y of t 0 to 1, and this will actually stop the solver when 1 is reached. In this case, the solution was an exponential. So you can also actually have custom actions here. Like you can print stuff just by saying rule delayed on that. And let's say, here t equals, and then let's just print the value of t there. And you get the value of t at which we went out of bounds. So yeah, this is definitely possible.
Excellent. Great. Thank you, Jim.
Sure.
We've got time, I think, for 2 more questions. So the next question, I'm going to go back to Sasha here. Sasha, what is the maximum precision that Mathematica can give for pi?
Well, that's a very good question. So I have to admit, I cheated a little bit when I said that in extended precision computation in Mathematica, we can take an arbitrary number of digits. That's really not correct because it's always limited, and it's limited by amount of memory in particular. But first, I want to get to the juice of the question and say that the Mathematica uses Chudnovsky formula to evaluate pi, and that particular formula gains about 32 decimal digits per iteration. The formula is stated right here, and the Mathematica, of course, can evaluate that. So the formula gives 1 over pi, which is then inverted. So you can ascertain that it gains 32 decimal digits by trying to do a logarithm and get that number evaluated. So you see that the asymptotic term of the asymptotic sort of behavior of the term is e to the minus 32k. So that's this, and now I want to sort of actually go and show it in the action. So using this Chudnovsky formula, we sum using the asymptotically fast binary splitting method developed by Brent. So we can say compute, well, 10 to the 6, it's cached, so it's instantaneous, but 10 to the 7 points takes 22 seconds, and 10 to the 8 point takes 347 seconds. So when we take a real number and represent it internally, it is represented as a sequence of binary words. And the maximal number of such words is 2 to the 64 minus 1. So that's a maximum representable integer number. So the total number of binary digits is this. And the corresponding number of decimal points is approximately 3.5 by 10 to the 20. Now, by doing a simple experiment, setting precision of 1 to 10 to the 8, we would approximate that should take approximately 1.5 times 10 to 11 gigabytes of RAM, and that will, you really need to take a very powerful machine to do that. But Mathematica should be, internally is capable of carrying out evaluation of pi to that many digits of precision. So, thank you.
Excellent. Thank you, Sasha. And like I said, we have time for one more question. This question is for Paritosh. And the question is, can parametric NDSolve take win event?
Yes, that's a very good question, and the answer to that is yes. And just combining parametric ND-solve with when event, you can do fantastic stuff. Let me go back to my notebook and let's come up with a synthetic example wherein this is demonstrated. So I'll set up a function from parametric ND-solve, and again I'll take something trivial but good enough to demonstrate what's going on. I'll take an initial condition. We'll set that to S. So S being my parameter. S goes from t to 0 to 1. I will put the when event now, and now I say when event x of t is, I don't know, 1.5 or 1.1, then x of t make it add, I don't know, 0.5 to it. Okay, and with that I'll generate. Let's introduce ND-solve value here. Okay, so there you have a numerical function. And now what you can do is take nf and we'll set the parameter to be 1. You get an interpolating function out of that. Let's put that in, plot. And you can see that right when we wanted it, as soon as it hit 1.1, I added a value of 0.5 to it. So then the solution, you basically get this beautiful jump. And with that, you can basically build on this and do fantastic stuff. Yeah, so that's basically the answer. Short answer is yes.
Excellent. Well, thank you, Paritosh. I just want to thank all of our panelists, as well as Rob on the phone, all the Wolfram staff who pulled this together, and very much you guys for joining us today. And we will see you next time. Thank you.